Hi, this lesson we're learning about resolution. This is lesson 10 of my playlist Waves and Wave Phenomena, and it is a part of topic 9, which is high level only. Let's start with these two images. Which one do you think has been taken with a camera which has better resolution? Obviously, the answer is the one on the left. So let's see how this works in physics. First, I'm going to show you the recording of a train approaching. As the train approaches, I'd like you to watch the headlights, especially this one, and observe how clear it can be seen as the train approaches. Did you see that the image got clearer and clearer as the train approached? It actually got more and more resolved. What are the factors affecting resolution of an image? The first one is the separation of the two sources to be resolved. The symbol we're going to use this will be lowercase d, and that's how I can show you on an image of the distance between two headlights of a car. Another factor that affects resolution is the diameter of the aperture receiving the light, which is b. This could be the diameter of a satellite dish. It could also be the diameter of the pupil of your eye. Another factor is the distance measured to the sources from the receiver. For example, Earth-Moon distance if we are observing the moon with a satellite. And the last factor is the wavelength of the light that is received. We're going to discuss each of these one by one to see how they impact image quality. The first factor we're looking at is the separation of the two sources, lowercase d. In this example, I have a source 1 here and a source 2 here. These represent the light ray coming from the centers of the two sources. This is the circular aperture that the light is collected with, and these represent the images formed by each source on the screen. The screen in the eye pupil case would be the retina of your eye. In the satellite dish case, it would be where the image is processed. In either case, the distance between the images and the circular aperture is estimated to be 0. That is this distance. So you should see that as the two sources are far away, their images also get far away. If the two sources are closer, then their images also get closer, which means it is harder to resolve them. Moving on to our second factor, resolution and the diameter of the receiver, which is b. Now, this simulation will allow us to change the diameter of the telescope. I'm going to use two values for this, 100 millimeter diameter and 600 millimeter diameter. So let's see. So this is the image of the moon seen with a 100 millimeter diameter telescope. Changing diameter to 600. and this is the image that that telescope can give. With a 100-millimeter telescope, looking at a point in the sky, compare that with the same region seen with a 600-millimeter diameter telescope. As you can see, increasing the diameter of the receiver increases resolution. So when the telescope or eye pupil has a larger diameter, the image gets more resolved. Looking at these two images, I have put the source 1 and source 2 at a fixed distance from each other now. I've used a small piece of rope to make sure that is constant. The distance to the receiver is the same, but the size of the aperture is different. You can tell this is a much larger circular aperture and this is a much smaller circular aperture. So the angle these make are different. Looking through a larger telescope, a larger aperture, the images seem to be more resolved. And if you collect the same light with a smaller aperture, then the images of these two sources are not very well resolved. The third factor we're looking at is resolution and the distance to the sources. So now I'm keeping their separation and the aperture the same, and if we observe the sources from a further distance, you can see that this angle is smaller, and if we observe at a closer distance, this angle gets bigger and the images actually move more away from each other on the screen, which makes them more resolved. Let's watch this again. Small d and large d.
We learned in the previous lesson about single slit diffraction that the width of the central maximum depends proportionally on the wavelength. So the longer the wavelength, like red for example, the wider the central bright fringe. As wavelength gets smaller and smaller, the width of the central bright decreases. We're going to use this information to understand resolution. So I prepared two of each, and I'm going to use these pairs with the mark of the zero angle position in their center to demonstrate how we can tell resolution. How do we determine that two images are just resolved? Basically, imagine the two car headlights. If the car is really far, the images of the two headlights might be too close to each other. If they are forming images, these are the images of the two headlights that are formed in our eyes. If the two images are like this, we can't quite tell if it is a car or a motorcycle, especially if it's at night. So as the car gets near, these images of the two headlights get a bit more resolved. But if this is the condition, we still don't say this resolved in physics. The limit for being just resolved is this. One image has its center at the first minimum of the other, and vice versa. If the car gets even closer and closer, these will keep moving further away, and now we call this well resolved. So well resolved, just resolved, and not resolved. Let's try this with green. I can demonstrate the same thing. Well resolved, just resolved, and not resolved. Let's add blue to this. Well resolved, just resolved, and not resolved. So, now that we have seen the condition for being resolved of two images, we can apply this knowledge to two distant stars, for example, or resolution of the image of the moon. For example, in the moon case, we would treat the two edges of the moon as two sources if those two images are obeying Rayleigh criteria, which is the center of one diffraction pattern coincides with the first minimum of the other, then we say the image is resolved. However, if our telescope is not powerful enough, then the image may not be resolved like this. Now, sometimes resolution improves by distance. That could be on a car case, for example. As the car gets nearer and nearer, we can tell the two headlights apart. So one way to improve resolution would be changing the distance to the objects that are being resolved. But in the star observation, we cannot do that. So what can we do to improve resolution of stellar objects? In that case, we can change the size of our telescope. A larger diameter telescope will have better resolution. Another way to improve resolution is to use a different wavelength. You can improve resolution with a smaller wavelength. And here is why. Let's say these are the 2 points of forming the image of the two sources. So one source forms an image centered here, and the other source forms an image which is centered here. Now the problem with red wavelength is the central bright is also large, so it's very hard to tell these apart because these are too wide. However, if I replace this with blue wavelength, for example, remember this is the location of the central bright of one image. Let's put that there with blue wavelength, and the other falls over here. Do you see, since the central bright width is smaller with a smaller wavelength, changing wavelength to a smaller one, for example, red to blue, will improve resolution.
Let's see how resolution works for two sources which are to be resolved. Now these two sources could be two distant stars, the two edges of an object, such as the two edges of the headlight of the approaching train at the beginning of this video, or the two edges of the moon. They might as well be two headlights of a car. We observe these two sources and basically collect the light through a circular aperture, which could be a satellite dish of a telescope, or it could be the pupil of our eye. I will label the separation of the two sources as small d, and I will label the diameter of the circular aperture as b. Looking at this diagram, these are the two sources to be resolved. Separation small d. Capital D is the distance to the sources from the aperture or the screen, because this distance is so small we can approximate that to be 0. This is the circular aperture that we observe from, and b is the diameter of it. Wavelength is the usual lambda. So for a circular aperture, the condition for being just resolved is given by that angle. This is called the angle of resolution, and on the diagram it's this whole angle. Obviously also on the other side. If the angle, if that ratio is equal to that ratio, the images are said to be just resolved. If that ratio is larger than that ratio, the images are not resolved. For making resolution improve, you have to look for ways to make that ratio larger or make that ratio smaller. This could be with a smaller wavelength, a larger diameter. Resolution could also be improved by a larger separation of sources or a smaller distance to the sources. The Rayleigh criterion. If the central maximum of one diffraction pattern coincides with the first minima of the other diffraction pattern, then the two sources are said to be just resolved. This is known as the Rayleigh criterion.
We have been considering the idea of resolution, looking at intensity diagrams. Let's see how we actually observe resolved or not resolved images on our screens. If these are the two intensity patterns of two sources, they are obviously well resolved. What we would be actually seeing is this. If the two images are just resolved, we would be seeing this. And if they are not resolved, we get to see that.
This image is how you would show the condition for being just resolved on paper. You can see the central maximum diffraction pattern for two sources given, and to show the just resolved condition on an intensity diagram for two sources, you must ensure that the first minimum of one pattern coincides with the central maximum of the other, and vice versa. The first minimum of one source coincides with the central maximum of the other, and this is what the image would actually look like. So let's summarize. The changes on each of these factors which increase resolution are as follows: decreasing wavelength, decreasing the distance to the sources, increasing the separation of the sources, and increasing the diameter of the aperture. And to summarize, the resolution angle is given as 1.22 lambda over b. When this ratio is equal to the ratio of the source separation to the distance to the sources, that's what we call a just resolved image. The image gets better resolved when the ratio on the left becomes smaller than the ratio on the right. Okay, here's an additional task before I move on to the actual homework. Anyone who has learned about resolution should also find out about the image of the black hole at the center of the galaxy M87, which was released in April 2019. Now, this is pretty huge in the science world, and I believe that if you research this, you will be fascinated by how this was accomplished. Search for the Event Horizon Telescope. That's it for this lesson. I'm gonna scroll through the homework questions and there will be a solution video as a follow-up.